Part 2 of organic chemistry is mainly just about isomers and some functional groups. So we're going to talk about functional groups in depth because they are very important. They totally change the reactions if you have maybe an alcohol or an aldehyde or a ketone or a carboxyl group, whatever it may be. It's going to change the reactivity of that compound. It's going to change the properties. It's going to change the compound's nature. So let's go ahead and get into isomers. Isomers are just a compound with the same exact molecular formula. So in our case here, we've got C4H10. But things are arranged differently. Their structures are different. So we've got molecules made of the same things, but their structure or their bonding patterns are different. So our first example here, we've got a 4-carbon chain, just straight carbons, all single bonds. So 4 is bute, that would be butane. And our second example here, we've got the longest continuous chain of carbons is just 3 carbons. So that's prop. All single bonds is propane. However, we've got one substituent, we've got one addition or attachment, that's our methyl group there, and the methyl is on the second carbon, so we've got 2-methylpropane. So though their molecular formulas are the same, they're made of the same stuff, their names are different. With these isomers here, I've actually already given you the answers here, but we've got some different structures that can be formed for the chemical compound C5H12. So the first one, you've got 5 carbons stretched out in a line, all single bonded. So that's our pentane. You've got the second example, which is very similar to our previous slide, where you've just taken one of those carbons off the long chain and added it as an addition or an attachment. So whenever you add an attachment though, if something's asking you to draw multiple isomers, you cannot put the attachment on the end or on the terminal end of either side of the long carbon chain, because all it does is add to the chain. It does not make it an attachment. So you've added it within the carbon chain, not on the ends. So in this case, we've got 2-methylbutane. The one over here on the far right hand side here, that's the more complex one. That one actually has shortened the carbon chain to 3 carbons. So we've got propane, because everything's single bonded here. But we've got 2 attachments. So those 2 attachments are on the second carbon, making it 2,2-dimethylpropane. It's a little bit harder because you've got to remember that you can actually form 2 attachments here. So when we talk about isomers, we're also going to talk about the geometry of these isomers, and so we call it geometric isomers. And so that just means their geometry, or the way they're arranged in space, their 3D nature, are going to be oriented a little different. And the only time that we ever talk about geometric isomers is whenever we have substituents around a double bond or a triple bond. So those normal alkanes, we don't talk about geometric isomers. But when we talk about alkenes and alkynes, we do talk about the geometric isomers. So when we talk about these isomers, we're going to talk about cis and trans, and these terms will make much more sense when I show you some pictures. But when we talk about substituents being on the same side of the molecule, we call it cis. When they're on the opposite side, we call it trans. So let's do some examples, and it'll help you make some more sense of this geometric isomer thing. So just to give you the first example here, we've got our normal old hexane, and there are some different images here you've never seen before. So normally I just draw hexane like this. Just 6 carbons in a line. But it's kind of a misnomer to call it a carbon chain or a line of carbons, because really what it is, it really actually looks like a zigzag. So you can see 3 different variations of the same thing. In organic chemistry, you will always draw it the lazy way, which is without actually telling me there's a carbon there. I have to understand that each point, you've got carbon, 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 carbon. 1, 2, 3, 4, 5, 6. So those 6 points, or the terminal ends, represent a carbon, and each carbon will be surrounded by its number of hydrogens. That's the lazy way of writing it, and this is how you'll see it. And it's the same way here. 1, 2, 3, 4, 5, 6. Same way here. 1, 2, 3, 4, 5, 6. These are those 3D molecules you'll get to play with some later. And really, it's a great example because there are orbitals, there are atomic orbitals or molecular orbitals around these carbon atoms. And they take up space. So things want to be arranged so they're not overlapping too much, because overlap would create double or triple bonds. Well, we have single bonds here. So we need to arrange things so that each carbon and all of its electrons has enough space to not inhibit the other ones. Whenever we go a little farther and we actually add a double bond, the double bond is going to create some geometric change. You can have two variations of this double bond, of this arrangement. So I've added a double bond right here in hexane to make it form hexene. So hexene, you have to tell me where the double bond is. So if you know you can't remember, you number the carbons 1 through 6, and wherever the double bond comes after, that's how you label its location. So we have 2 hexene here, and we have 2 hexene here. Now, the reason these are different is because of the geometric or the orientation of how they are around the double bond. So if these 2 carbons, you can see that are within the double bond, wherever this lies, this continuation of the chain and this continuation of the chain, they actually lie opposite of each other. So this one is below the double bond and this one is kind of above the double bond. So since they are opposite of each other, that's called trans. So if you were given this exact structure, you would have to tell whoever it was or on the AP exam, you have to tell them that is trans 2-hexene. Just saying 2-hexene doesn't tell them you understand why this is arranged in this orientation. So you also have the opposite of that. You can have something that looks a little bit different, where you've got your carbons here that are within your double bond, but your orientation has changed. Orientation is above that carbon, and the orientation of the continuation of this side of the carbon chain is also above that carbon. So because both ends or both continuations of the carbon chain are above, they're on the same side is cis. So if you were given this formula or this structure, you would write the name as cis 2-hexene. And that's really specific. Now, the only time you'll ever have to write cis or trans is if you were given the structure, or if they said things are on the same side, or the continuations are on opposite sides. So if you know it, you write it. If you don't know it, or if you don't see it, there's no reason that they would expect for you to know if the orientation is on the same side or on the opposite side. So you'd have to be given some more information. So this is rare. You only have maybe 1 or 2 questions like this. So just a refresher here, let's go back up. Trans is opposite sides of the orientation on the double bond or triple bond, how it's arranged in space, and we call that trans 2-hexene. So this is a slightly different example, but we're going to talk about butene now. So we have our 1, 2, 3, 4 carbon chain, and the continuations of the carbon chain are on the same side. It's cis. If they're the continuation of the chain, here's the double bond, continuation of the chain, are opposite of one another, that is trans. So like you transport something, you bring something across, you transatlantic bridge, trans, you should all know, means opposite. And then here's just a molecular format of what the same thing would look like in 3D format. We also have, some more complex versions of this cis-trans nature. So the geometric isomers can get a little more complicated, just like our other nomenclature got a little more complicated. Looking here, we're going to go ahead and name this. And since it is drawn specifically that you have continuations of the carbon chain below that double bond, both of them, we're going to have to name it with the appropriate prefix. So we're given this molecule, we need to do our normal, count up the carbons, which is the longest chain. So I'm going to count 1, 2, 3, 4, 5, 6, 6, or if I went down to this one, that would be 6 as well. So I've got a hex here. So hex, I've got hexene because it's a double bond. So we've got hexene. We got to tell someone who's looking at this where this double bond resides. That would be 2-hexene. Okay, but we're not close to done yet. We have this carbon chain. And we have some substituents hanging off, and actually only one. So this is our substituent. We have a methyl group. And the methyl group is going to be not prioritized here, where our double bond is actually prioritized, so we label our carbons according to the side where the double bond, its location is. So 1, 2, 3, 4, 5, 6. Therefore, our methyl group is at the 5th carbon. Putting this together, we also need to include at the actually in the middle here, I'll show you. We include the very beginning our substituent, just like normal, 5-methyl. And then we're going to talk about the double bond. And when we talk about it, we're going to tell the geometry as well. So since these are on the same side, this geometric isomer's label is cis. This is where we put cis in, and then we go ahead and finish off the 2-hexene. So cis goes right before you add the information about the double bond. This one is a long one. So you've got the name given to you, you've got information about the geometry of it, and you've got your normal information about substituents and how many carbons are in the longest carbon chain. So the first thing we're going to do is go ahead and draw out decene. Decene has a double bond at 3, and it's trans geometry, so that means it's going to be across from each other. So I'm going to go ahead and draw my double bond, and I'm going to add carbon, carbon. So I have 1, 2, 3, showing my double bond at 3. 4, well, let me draw this a little bit different. 5, 6, 7, 8, 9, 10. Oh, I don't want to add all those hydrogens in just yet. But when I count, I'm going to label these. So I have 10 carbons. My double bond was prioritized, so it had a lower number. This is our starting point. This is our carbon chain. When you go ahead and add in our substituents, our methyl is at at carbon 9. And we have 2 chlorines at carbons 3 and 4. So I'm going to put chlorine and chlorine. So you can see that the continuation of each side of the carbon chain, those are opposite of one another. That means it is trans. So if we had to, we could put in all the hydrogens as well here. So every empty space, of course, hydrogens need to be added because every carbon needs 4 bonds. All right, so we've talked about trans fats. You've heard about trans fats. Everybody probably intakes trans fats, which are not good for you. So just to give you some biological information about trans fats, the only thing that differs between trans fats that are unsaturated or saturated is just based on the hydrocarbon chain. So we have cis and trans. So we've got, at this very beginning, we've got a saturated fat because all the carbons throughout here have single bonds, and single bonds represent saturated fats because it's saturated with hydrogens. So all these little carbons would have their hydrogens added to them. This one, however, is not saturated. It's not saturated because it's not totally saturated with hydrogens due to the fact we have a double bond. And that double bond makes it unsaturated because that double bond's taking up place for some hydrogens to be located. And since this end of the carbon chain is below and this end is above, it's trans, which means opposite. So our trans unsaturated fat actually are very bad for you. because this weird, strange shape can sometimes be hard for us to break down. Our body cannot attack that double bond very well to break it down and use it for other things. And so it gets stuck in your body, and since it's sometimes seen as a poison or a toxin, it's not good for you to keep in your body. And then also, you can see the difference between trans and cis, with both sides of the carbon chain being below that double bond. That would be cis. Just to give you a little biology there. All right, so continuing, we've got to talk about cycloalkanes. Cyclo, you think like a circle, and that's pretty much what it is, a closed ring of carbons. So all of these are biological molecules that contain cycloalkanes, or are cycloalkanes, because they have some cyclical combination of carbons in a ring. You've got cholesterol, testosterone, and the DNA bases. So adenine, thymine, guanine, cytosine, they all contain cycloalkanes because they have these closed rings. So there's lots and lots important in biology. When we talk about cycloalkanes, we actually have to know how to name those as well. So it's really easy. If it's an alkane, it's got all single bonds still. So you can recognize it as single bonds and it's closed. And all you do is add cyclo to the front of the name. So cyclohexane, 1, 2, 3, 4, 5, 6. Carbon all the way around. And I told you this was the lazy way because we don't ever write the carbons actually in organic chemistry, because there's so many carbons, you don't have to write them all. You can just recognize it as a point. So if it's cyclo in the front, represents a circular shape. A very, very, very important cycloalkane is the one called benzene. They're called aromatic because they're very volatile, and a lot of times we'll talk about benzene a lot. You may even see this as an AP example on your test, because if you don't know what benzene is, they'll know that you did not remember your organic chemistry. So you have to know what benzene is. It is anything with this formula, C6H6. So 6 carbons with 6 hydrogens on it. And it's so unique because whenever you have this 1-to-1 ratio of carbons and hydrogens, what the structure looks like is a double bond at every other bond on this cycloalkane. So this is one way to write it, and this is another way to write it, because technically we could write this with the double bonds on the other, between those other carbons. So these are called like resonance structures. And this one with the circle in it is the lazy way to write it, due to the fact that those double bonds can be anyway as long as they are one after the other, so every other. All right, so we're going to start talking about the functional groups. These are the functional groups that we're going to learn about: the alcohols, ethers, carboxylic acids, aldehydes, and ketones, which kind of go together, so I'm going to group them together. We may talk about esters in a lab later this year too. So these functional groups are attached to the long carbon chain, and they make it not just a normal hydrocarbon. They make it, in fact, very, very different than any other hydrocarbon. And it's because of these functional groups having some special property, some special melting points, some special reactivity point. And they're not just like any old alkyl groups, like a methyl group or an ethyl group or a propyl group. They're very special, so let's talk about those. We're going to talk about alcohols. I briefly mentioned what an alcohol was in the previous PowerPoint, but let's go ahead and go back over that. The only thing that you need to know about alcohols are they just have a hydroxyl group on it, that OH group. So hydroxyl groups are just OH groups that are attached to the main carbon chain. So this R group represents the main carbon chain. It's easier just to write the R there to represent any carbon chain that you could possibly see. These are the most simple because all you do is attach the the OH group to one end of a carbon. And you have to tell me where the carbon is that you've attached this to. It could be in the middle, or it's usually at the end. Whenever you name them, you drop the E from alkane and you add OL. You add all, like methanol or ethanol. For example, if you saw this condensed structure, you would name it by what its carbon chain is, which is prop. This would be an alkane because they're all single bonds there, and instead of putting propane, you put propanol. Ethers are different. They actually have two sides of the carbon chain, and the thing that breaks them up, or the thing that attaches them together, is the embedded oxygen. So R prime is the longest carbon chain in the molecule, and the oxygen is connecting that to a shorter carbon chain. So R is the shorter of the carbon chains. Whenever you name these, they're named very specifically. So you have root for R, so maybe it's meth. You got oxy as the suffix. No methanol, no methyl, no methane, nothing like that. This is your suffix, and then you're going to add the second R group. So add that name. Here's our example. You look at it and you're a little confused because you've got all these weird substituents, but all you need to do is do like you normally do. You look for the interesting stuff. Well, right here is our oxygen that's embedded, and that's going to be connecting two carbon chains. So that's important to note. And then you need to find your longest carbon chain, just like normal. 1, 2, 3, 4, 5, 6, 7. There's 7 that way. And if you look, you'll see that that is the longest carbon chain, and there's no other way that you need to consider. So there's our carbon chain. And this group right here, this ether, it doesn't have any priority. It makes things very special. It makes this a special functional group, but it doesn't take precedent over any of the other attachments. It's going to be a different story for some other functional groups, but for these ethers, we don't have to prioritize this O. So we're going to start actually on the side that contains the most substituents. So starting 1, 2, 3, 4, 5, 6, 7, numbering from the right. This methyl group gets number 2, and this methyl group gets number 3, and then we'll name this chain as well. So whenever we looked here, we said this was hep, so this is 7. And we also saw that we had 2 methyls, so we have dimethyl. And those methyls are on 2 and 3. And the very first thing, if you look back at your previous slide, you put the root for the short chain first. So the short chain is this right here. 2 carbons is ethyl, or F. So we've got F. But we don't have the normal F, we have ethoxy. And where is that F present? It's off of the 5th carbon. So we have 5 ethoxy. And that's pretty much all we need to have, and we're actually going to put that into action now. So pulling this together, same thing as normal, you're going to be using alpha order. So looking at F and meth, F comes first. So you've got 5 ethoxy, 2, 3 dimethyl, and then there's the continuation of the name, which is heptane. There were no double bonds in here, so I just included heptane. So alpha order, E, M, heptane. All right, so that was ethers. We're going to go into carboxylic acids now. Carboxylic acids contain a very special functional group, which is the carboxyl group. And the way that is written is, this is how you will see it. You're going to see a carbon with a double bonded O and an OH group. So we've got the double bonded O and OH group on the end of the molecule. You have to see that to know that it's going to be the carboxylic acid. Whenever you name it, you add oic acid to the end after you drop the E from an alkane. Now this one has precedence. This one has a priority. The C in the carboxylic acid is the number 1 carbon. Memorize it, you have to know that, because if not, you're going to be numbering the carbons wrong and then we'll be drawing the structures wrong. So in this example, we've got a telltale sign right here that that's the carboxylic acid. That's the C double bonded O OH group with the rest of the hydrocarbon on the left-hand side. So automatically, you know that's carbon number 1. So that's carbon number 1. We're going to go ahead and find the longest carbon chain, just like normal. 1, 2, 3, 4, 5, 6. So that carbon chain is hex. I don't see any double bonds in the carbon chain, so that's hexane. Now, we also have a substituent, which is that methyl group. And that methyl group is off of carbon number 3. Now, because of this group right here, we've got oic acid. And where do we add oic acid? We add it at the end. So let's go ahead and write out our structure here. So we've got 3-methyl, and then continuing with the normal name, hexane, but here you want to put hexanoic acid. So oic acid is taking place of the E in hexane. Aldehydes and ketones have another similar group, but it's called a carbonyl group. So the carbonyl group looks like this, and you'll see 2 sides or just a single side that is a continuation of the carbonyl of the carbon chain. So you'll see different ones, but the carbonyl group is the one with just a C double bonded O, and it's present in both ketones and aldehydes. So here's the difference between those 2 types of functional groups. The aldehydes will contain the carbonyl group with a hydrogen as one attachment. So just like I showed you here, you end it with a hydrogen. The ketones are a little bit different because they are within. They're within a carbon chain. So this is a little messed up here, sorry. This double bond is right here with that carbon, and there's a continuation on the left and the right of the carbon chain. So we call this terminal, because it's at the terminal end of some hydrocarbon. Aldehydes are going to be named differently than ketones, just like any old different functional group. So the parent name is going to be including the C of the carbonyl group. So this C of that C double O, or C double bonded O, will be included in the parent name. We're going to include it in butanol or bute, whatever it may be. Whenever you add the suffix, though, you drop the E and you add AL as in pal. So like, we'll give some examples here in just a minute. Pentanal, maybe. The carbonyl C is number 1. So yet again, we have to make that a priority. So you don't have to include the number of that aldehyde, the location in the name, because everyone's going to assume it is number 1. So don't say 1 pentanal, because it's going to be number 1. It doesn't matter. So with our example here, this is our aldehyde group. So you've got C double bonded O H, and then the R group over here to the left. Counting up, who's number 1? Number 1 is that group right here. So 1, 2, 3, 4, 5. Starting with the aldehyde over here, our carbonyl group, we've got 5 carbons, which is pent. And you would like to say pentane since it's all single bonded, but you know that this is not pentane because it's pentanal with the AL ending because of the aldehyde nature of it. So beware. You see this? Don't see that as OH because it's not an alcohol. It's H with a double bonded O. Ketones are slightly different. So we're going to end the name here in "-one", as in tone. So ketones have an O ending, own ending. And also, again, the carbonyl group is given the lowest number possible, so that C is going to be number 1 and the C double bond O. Now, there are some differences between aldehydes and ketones. Because of the fact that we've got, I'm going to back up for a second. I maybe even told you. Forget that that's going to be number 1. It's just going to have the lowest possible number. If it were number 1, it would be an aldehyde because it would be on the terminal end. Sorry about that. We're going to have 2 sides to this, so we want to make this the lowest number possible, and start on either side with the shortest number of carbons on the left or the right. I'll give you an example here. So looking at this ketone has got this double bonded right here to this O. It is within the carbon chain, and so we're going to start on the side that the ketone exists. The ketone is on the right-hand side, so numbering our carbons 1, 2, 3, 4, 5. Our ketone has been prioritized so that it has a low number, but in this case we must tell the number of carbon for that ketone. So we have to indicate the location because it could be anywhere in between. We just don't know where. So here we go. We have to name it 2-pentanone. So the one you'd want to say 2-pentane, but you change the E to O-N-E. And there are 5 carbons, like we said. All right, take a minute, pause the video, and I want you to look at this and figure out if this is an aldehyde or a ketone, and see if you can determine the name. So I'm going to pause this for a minute, and then you can start it back up whenever you're ready. All right, hopefully you figured this one out by now. So since this weird functional group is within a carbon chain, that carbonyl group is within a carbon chain, we've got to know that that is a ketone because it's not terminal, it's within. So numbering, prioritizing the ketone functional group, we're going to number from the left. 1, 2, 3, 4. So our longest carbon chain is 4, which is bute. And the substituents are methyl groups, so one right here, one right here. We've got dimethyl. Both methyls are on carbon number 3, so we have 3,3-dimethyl. And when we put that together, we need to recognize the location of the carbonyl, or the double bonded O. So that carbon is number 2. So we're going to have 2-bute, but then you need to know the suffix of the ketone, which is butanone. So put it together as 3,3-dimethyl 2-butanone. This is a lower number, so we have prioritized that carbonyl group. Take another second, pause, and see if you can figure this one out. You're going to see some differences here, and see if you can also determine the name of the compound. All right, hopefully you figured it out, and you see this structure on the end, which is the weird thing that you have to be aware of. It's not an OH group, it's an HO group, which will be our aldehyde. You also see some methyls hanging off and a double bond. So we've got a lot going on here. We're going to go ahead and prioritize the carbonyl carbon. Carbonyl carbon is the C at the end here, where we have C double bonded O in the aldehyde. So this is number 1. Continuing 2, 3, 4, 5, 6, 7, 8 means we have oct, because we have 8 carbons, and we have a double bond. So it's not octane, it's octene. So I'm going to write that there so I don't forget that. That's going to be octene. We also have to recognize where the double bond is. Well, double bond is after carbon number 6. So we have 6 octene. And all we've done so far is just describe that carbon chain, nothing that's attached. So we have methyl groups. We've got 2 of them. So we have dimethyl 3 and 7. Because there are 2 different locations. To show that we know there's an aldehyde attached, we change the ending of "ene" to something else. So we call it octanol. Make sure you show that E in AL. So to continue and finish this up, 3,7-dimethyl. Recognize the double bond at the 6th position. Octenal to show our aldehyde. So when we do our prioritizing the numbering of the carbon chain, we do have to always recognize the carboxylic acid carbon, which is the C double bond O with the OH on the end. That carbonyl C in aldehydes and ketones. So in the ketone, we're going to prioritize and make it just the lowest we can. In the aldehyde, where it's terminal, it'll be carbon number 1. And then we have our double and triple bonds. We also always want to prioritize, but those functional groups are very, very special and they're very important. So that's why they're prioritized over the alkane-alkyne double and triple bonds. And then any of those other substituents, the alcohols, which are the OHs, or the methyl groups, just those alkyl groups. Those are the last of our worries, and we're going to number those after we've numbered and prioritized these other ones. Lastly, you've got some practice. So you're going to try some examples on your own. These are the functional groups. They're important. Try these. I'll have the recording of the solutions on a separate video. Good luck.